Welcome to this video series on how to design an impact wrench adapter for use with a cordless drill. In this video series, I will cover the engineering of an adapter to transform a regular cordless drill into an high-torque impact wrench for a so-called free project as a mechanical engineering student at HAN University of Applied Sciences. I need to mention that it is much more cost-effective and efficient to just buy a cheap impact wrench instead of going through all the trouble to make it yourself. But for the sake of engineering and the study credits for the free project, I decided to design one myself and meanwhile show you everything involving the design process. Instead of engineering a complete impact wrench, I decided to limit the design to only an adapter that contains the impact mechanism, which can then be used with a regular cordless drill. The software that I am going to use for the engineering process is MATLAB Simulink for solving a simple dynamical model in the early design phase. I will be using Siemens NX for drawing the 3D CAD model and simulating the dynamic impact. I will also be using Excel for doing iterative calculations instead of doing these by hand. One of the first steps in an engineering process is drawing up the requirements for the design. In this case, the requirements I have drawn up are as follows. The diameter of the drive shaft is a maximum of 13 mm to fit inside the chuck of the drill. The adapter has to fit in one hand when holding it. With my own hands as reference, I chose a maximum diameter of 80 mm. The weight is limited to 2 kilograms. So it is not too much of a burden to hold. It is possible to manufacture inside the workplace at the university. I will not go into too much detail here, but simplicity for production of the parts is preferred. A cordless DC drill with a maximum torque of 12.5 Nm and a maximum speed of 1,500 RPM is used as reference. The output torque is to be maximized for the given limitations. Some requirements can be interpreted freely, which is not something you would normally want. This list of requirements will do for this example, but in a real project some requirements must be specified in a more specific manner. However, you should know that a design process is almost always an iterative process, and as the project progresses you will discover new things and perhaps draw up new requirements. Now, for this design it is important to first understand the physical principles of how torque and speed of the motor is converted into higher torque bursts. This can be explained by two physical laws and equations. These are Newton's second law of motion and the law of conservation of energy. Newton's second law of motion, for in this case rotation, states that the net torque is equal to the mass moment of inertia of the rotating object times the angular acceleration of the object. The second equation is based on the conservation of energy, which is in this case the rotational kinetic energy. The rotational kinetic energy is equal to 1 over 2 times the mass moment of inertia times the angular velocity squared. The electric motor of the cordless drill provides a torque that accelerates the hammer flywheel and increases the speed at which this rotates, the so-called angular velocity. The hammer then comes to a stop by slamming into an anvil and transferring a large portion of the rotational kinetic energy in a small amount of time onto the square drive for socket tools. The rate at which the flywheel accelerates depends on the torque provided by the motor and the mass moment of inertia of the flywheel itself as described by Newton's second law for rotation. The mass and geometry of the hammer flywheel do not change, so the mass moment of inertia is a constant. However, the torque provided by the cordless drill is not constant. This is a typical torque speed curve of a DC motor. As you can see, the torque of the motor changes with speed. The maximum torque of the motor is the so-called stall torque, which is at 0 RPM. The maximum motor RPM is called the no-load speed, since no more torque is available for further acceleration or other loads. In order to maximize the torque output, the kinetic energy at impact should be as large as possible. This can be achieved by dimensioning the hammer flywheel so that the mass moment of inertia is as high as effectively possible, but increasing the mass moment of inertia will eventually cause the angular velocity to decrease, because the motor can only supply so much torque as explained before. More effective would be to increase the speed at impact since this is squared in the kinetic energy equation, but this is also limited because of the maximum motor RPM. The next video will go into more detail. Now we know the basic physical principles of how an impact wrench works. The next step in the process is to decide which mechanical mechanism to use in the impact wrench. This can either be based on an existing mechanism or a completely new one, but you should check in databases, such as a SpaceNet, if a particular design is not patented before you use it for your own design. There are several types of existing impact mechanism and each has its advantages and disadvantages. I will not cover all these types of impact mechanisms in this video, but I will provide a link to a video that covers a few examples for pneumatic impact wrenches. The mechanism I chose for my design is most common for electric impact wrenches and can best be shown with this animation. The main driveshaft is powered by the drill and contains two V-shaped grooves. The flywheel hammer is positioned on the driveshaft and also contains two V-shaped grooves pointing in the opposite direction. A hardened steel ball is placed in both grooves to connect the driveshaft to the flywheel. The flywheel can now rotate and slide up and down on the driveshaft. The mechanism also contains a spring to prevent unwanted sliding of the flywheel hammer on the shaft. Because the spring exerts a force on the hammer in the direction of the anvil, the rotation of the driveshaft is transferred into rotation of the flywheel hammer by the ball in the bottom of the V-grooves, almost as how a keyed shaft works. However, the angle of the V-shape also allows up and down sliding of the flywheel hammer on the driveshaft. This is useful for retracting the hammer over the anvil after impact, as the tangential force component of the motor torque overcomes the force component of the spring when further rotation of the flywheel hammer is blocked by the anvil. The flywheel also has two hammers on opposing sides, which means that there are two impacts per full rotation and that the impact load is distributed over two sections. This also means that there might be less kinetic energy available to be released at each impact, so the output torque is lower than when you would have one impact per rotation, but this depends on the size of the flywheel. The reason for choosing this mechanism is the relative simple design and fabrication of the metal parts by manually turning and milling. Only the V-shaped grooves and the hammers on the flywheel would have to be CNC milled due to the more complex geometry that requires simultaneous control of the 2 or 3 axes. Another advantage of this design is that the potential energy that is put into compressing the spring is also partially released again as rotational kinetic energy through the slope of the V-grooves. This increases the impact energy and thus the output torque. In the next video, the dynamical calculations that are necessary to determine the size of the flywheel will be explained. This will include solving a dynamical model in MATLAB Simulink. We will also cover the calculations that are needed for dimensioning the V-grooves, shaft, and spring.